All right, in this video, I'm going to cover section 2.5, conditional probability. So here, you can see that conditional probability is denoted by P of B bar A. What does that mean? So that means probability of B given that event A is already occurred. So we assume that event A is already occurred. So um, that effect on the probability of event B. So let's see example in the textbook. So here, let's see right here. So this communication channel has an error rate of 1 bit per every 1,000 transmitted. So errors are rare, but when they occur, they tend to occur in the bursts that affect the many consecutive bits. So if a single bit is transmitted, we might model the probability of an error as 1 over 1,000. However, if the previous bit was in error because of the burst, we might believe that the probability of that the next bit will be in error is greater than 1 over 1,000. So as you can see that the previous error will affect the probability that the next bit will be in error, right? So this is example of conditional probability. So now I strongly recommend that you read the next two paragraphs with the figure. So let me skip it. So now example 2.17. So let me before going over example 2.17, there are two ways to calculate the conditional probability. But the first way is to change the sample space. The sample space. So I'll tell you in detail by using the example 2.17. Okay, so example 2.17, surface flows and defectives. So you see table 2.2. So this table provides an example of 400 parts classified by surface flow and as the functionally defective. So for this table, the conditional probability match those discussed previously in this section. For example, so look at this. Of the parts with surface flow, 40 parts. So we see here, how many, give me a second, how many parts uh, has a surface flow? It's 40, right? Total, we see here. Okay. So now 40 parts, the number of defective one is 10. Yeah, so out of 40, 10, right? So therefore, probability that the event D, I mean, the parts with surface flows is given that the parts is only defective. And then, well, think about this. When we a second, we're here. So when you figure out the probability of D is what? Actually, this is gonna be total number of the total number of outcomes in event divided by number of outcomes is sample space. What's a sample space? I mean, what's the number of outcomes in sample space? 400, right? So we're talking about 400, right? So see that right here, 400 total. So 400, okay. And then top one, how many outcomes in the event? I mean, how many parts has surface flows? 40, right? Okay. So that's the probability. But now when you calculate this one, so you can see that in the fraction, the denominator has been changed. Not the instead of the total number of outcomes in sample space, the we put the number of parts is what as the defective. Let's see right here. This one. We want to find out uh what number of the what give me a second right here. So give me a second. So here, sorry, it should be, give me a second. Uh, yeah, okay. Sorry. So here, probability of the D defective is going to be the total number of outcomes in sample space, which is 400, right? And then numerator going to be, sorry, not 440, but you see the 28. You see that? That's the total number of outcomes in event D, defective, right? So should be 28. Okay, just 28. But here, when you find the conditional probability P of D bar F, so first one, the total number of outcomes in sample space will be reduced because of event F already occur. So we wanna find out. We need to find out what the part has surface the what we wanna find out the parts which is defective also has surface flows. Okay, so the first one, we'll see that this one. This is the total number of outcomes of the event F, which means that that's going to be updated sample space, which means that that's the number of parts has surface flows. Okay, so the total number of outcome sample space will be reduced, satisfying the event F, and then we want to find out the parts. I mean, in out of 40, we're gonna find out the number of outcomes in the event D, which is a part which is defective under the assumption that the parts has already surface flow, so which is 10. Okay, so that's the how to find out conditional probability. Okay, and then the parts without the surface flow 360, the number of defective one is 18. Yeah, so that's going to be probability D bar F prime. So what that means, this is a probability. We're going to find a probability that the part is defective given that the part is doesn't have surface flow. Okay, so now then how many parts doesn't have a surface flow? 360. Okay, so now we see that the total number of outcome sample space will be replaced by 360, and then the how many parts is defective, but parts doesn't have surface flow, 18. So we'll find out the parts which is defective out of 360, not 400. So which is 18 over 360. So that's the one way to find out conditional probability. And then the second way is to use the formula. So this is a formula of the conditional probability. So conditional probability of an event B given an event A denoted as P of B bar A is like this. The numerator is a probability of A in a section B over probability A. So um, sometimes we gonna use, I mean, I think later we gonna use this one. We're gonna use this one to find out probability A in a section B. Sometimes conditional probability is given, and then we know P of A, and then we don't know the numerator probability of A in a section B. Then we can use this one by what? Isolating the numerator probability of A in a section B. So we'll see this one in section 2.7 and 8, by the way. So see, now let me see. What about this? The definition can be understood in a special case in which all outcomes of random experiment are equally likely. So we're gonna assume that all random outcomes are chosen randomly, okay? So that each outcomes has an equal the probability of the each outcome is equally equal, okay, as 1 over n. So now then, the probability of A intersection B going to be number of outcomes in A intersection B over n. So what that means, so see example it is 2.18. So again, consider 400 parts table 2.2. From this table, so I'm going to use the formula of conditional probability. Then P of D bar F going to be P of D intersection F. So we're going to find out probability that the parts, I mean, we're going to find out all total all of the parts has, okay, what? The surface flow and defective is defective. So which is what? 10, right? You see that? 10, yeah, let's see that. So this many of parts is defective and has surface flows out of 400. So 10 over 400, that's the probability of D in a section F. Divided by P of F is not a big deal to find the P of F because this is not a conditional probability. So we're gonna find the total number of outcomes F, which is 40, right? So 40 parts is defective, right? Divided by, let's see, a second. So you see that here, 40. This is the total part, which is surface flow. I'm sorry, surface flow, right? Surface flow divided by total number of outcome sample space, which is 400. So 10 over 400 divided by 40 over 400. This is nothing but what? This is practically, this is 10 over 40, right? Note that in this example, all four of the following probabilities are different. So yeah, let's see. So that's what we have figured out so far, right? So now then, what about this? P of D bar F is 10 over 40, and the P D prime, I mean, complement of D bar F is the 30 over 40. It makes sense. So now, and then this one, let's see. P of D F prime going to be 18 over 36, and then P of D prime bar F prime is 342 over 360. So I'm sure that once you understood this one, P of DF, okay, and then all, I mean, P of D and P of F bar D, then it's not a big deal to figure out, you know, those four um, the conditional probability. Okay, so now, so that's what we so this is the what diagram of the local conditional probability. Okay. So now what random samples and conditional probability. So what's a random sample? To select the randomly implies that each step of the sample, the items that remain in the batch are equal like to be selected. So see, look at this. Let me see. Let me see right here. Okay. Give me a second. So here, the to understand the random samples, we need to look at these examples. So the here we're gonna the what? So let's look at this. So yeah. So simply saying the random sample is this. Even uh the even if we select the one outcome, we select the one outcomes. I mean one outcome. Um, we select the one outcome in the sample space. So sample space is and then replacement is not allowed. So replace the size of sample space is reduced. The still the probability of each outcome is equally likely. So yeah, so look at this examples. So this is talking about the conditional probability uh, of the sample regarding sample space without replacement. So the let's see. Okay, so here, for example, okay, so let's see. When a sample is selected randomly from a large batch, and it is usually easier to avoid the enumerations of the sample space and calculate a probability from conditional probability. So for example, suppose that a batch contains 10 parts from tool 1 and the 40 parts from tool 2. If two parts are selected randomly without replacement, what is the conditional probability that the part from tool 2 is selected second, given that the part from tool 1 is selected first? Okay, so then let's see. So let's say E1 is let's see the event that what? Let me see. Okay, give me a second. Oops. So E1 is a tool. Let's say the parts in tool 1. E2 is a parts from parts from tool 2. Okay. So now then let's see. Okay, let's figure out probability that we choose a tool from part from tool 2, given that we already got a tool parts from tool 1. I'm so confused. I'm sorry. So now then, P of E. So okay. What are we gonna do? We need to figure out what first one, and the replacement is not allowed. Okay. So then, let me see. Ooh. Okay. So since think about this, E1 is already occurred, event E1. It means that we already what took part apart from tool 1. So how many parts are left? 49, right? So how many parts in total we had? 50, right? So what 10 from tool 1? Let's see. Oh, let's see. Okay. So 10. You see that 10 parts from tool 1, and then 40 parts from tool 2. You see that? So total there were 50 parts, right? But we already got one part from tool 1. So and the replacement is not allowed. So anyway, not allowed. So the total number of outcome sample space is reduced by 49. You see that? So 49. So and then we're gonna figure out how many the number of way to select the what part from tool 2. Out of 49, how many parts belong to tool 2, second tool? 40, right? So that conditional probability is going to be 40 or 49. Okay. So now, so yeah, in this manner, we can figure out P of E. P of E is equal to P of E2 bar E1 times P of E1. Why? Because we know that by the formula of conditional probability, this is equal to what? P of, see that, E1. One intersection. Oh, so hard. Okay. Please understand that my writing ugly, so I'm not familiar with the writing using mouse. Okay, probably E1. Okay, so now then, okay, so times P of E1 is what? So that fraction P of that conditional probability is nothing but that fraction times P of E1. Then this is nothing but P of E1 intersection P E2. So what is the event E? You see that event E consists of outcomes with the first and selected part tool 1 and intersection, the second part from the tool 2. So probability that that we select the parts from E1 and E2, it's gonna be what? Okay, so we see is equal to this one. So it means that what? So that's I told you. So that's what I told you. So sometimes we can use the formula of conditional probability to find out what probability of the intersection. Okay, that's example of the case. Okay, so we already got this one, which is 40 or 49 conditional probability times P of E1 is what? The number of outcomes E1 is 10, right? There are 10 tools, 10 parts in the tool 1, right? So 10 over 50. So multiply that fractions, we're gonna get 8 over 49. Okay, so that's the 2.5. Okay, so let me stop here. The next time next video I'm going to cover section 2.6.